And here we are. Hello. Does that work? Okay. So for those on the call, you probably didn't hear much of that, but in a nutshell, I work in a bank. I'm not a banker. I come from the academic world, but I am one of these subject matter expertise that Nuni was speaking of. So I've got some content to go through today to tell you what the bank is thinking about the hydrogen picture and the outlook. We're obviously a commercial bank, so we're looking for commercial opportunities. But as Nuni said, why do we care about hydrogen? Why have they employed someone in the hydrogen space and the others in our team? So we have carbon capture experts, we have agriculture experts. It's because we know that we have to get to net zero. The bank has made big commitments in the space. So we've said that we're going to get to net zero by 2050. We've also said that by 2030, we're going to have some interim financed emissions targets. So based on the emissions of our clients, so we fund people in the oil and gas sector, the power and utilities sector, we've made a commitment that by 2030, we need to be seeing our clients come on a glide path towards net zero to reach our commitments. And we know the way to do that will need a bunch of technologies. We know that electrification is going to play a huge role. So electrification is going to do a lot of heavy lifting in the route to net zero. But we know that electrons can't do everything. Sometimes you need a molecule, and that's where things like hydrogen will come into play. I'll go through a few details in the slides, but basically where the energy density of electrification through battery electrification, for example, falls short, or if you need a molecule for a chemical reaction, you can't use electrification. So we know that these technologies are going to play a role. And in a nutshell, this is my one slide that I use at the bank to say, why do we care about hydrogen? So in the top left, we can see that it's not new. We use hydrogen. As Rena was saying at the start, there's different colors of it. We're trying to move away from color classifications and move more towards carbon intensity thresholds. But practically speaking, everything at the moment is gray. So we use 95 million tons a year of hydrogen, mainly in refining. You see the dominant sector here, but also in ammonia. So we'll go into a bit more detail later on, but we use hydrogen into ammonia to make fertilizer. Some of it in methanol, so a lot of chemical process industries use hydrogen at the moment. But at the minute, it is grey, and grey means it's made from fossil fuels with no abatement, so no carbon capture. So in the bottom left, we can see that 95 million tons a year. If you multiply it by about 10, you get 950 million tons of carbon emitted per year from current uses of hydrogen. Because most of it, globally speaking, on an average, most of it is natural gas without carbon capture. Some of it is oil, some of it's coal, that's mainly in China, but global average, most of it comes from natural gas. So if you think natural gas is predominantly methane, methane is carbon and hydrogen. The way you do it is you use steam methane reforming to split that bond. You've got the carbon that comes out, the hydrogen that comes out, you use the hydrogen, and then the carbon is just emitted. So one way to reduce those emissions is to use carbon capture, and that's blue hydrogen. So it's the exact same process, but you try and capture the emissions that come off it. Theoretically, you can get up to maybe 95% or high 90% capture rates. In the real world at scale, more realistic, maybe 60%, 70% capture rate. So there's still a lot of research that needs to be done in different kinds of sorbents, different kind of reaction mechanisms to capture that carbon. So that's the here and now. Electricity is where we want to be working towards ultimately. That's using electrolysis, so splitting water, H2O, using, if you think back to like science at school, you had two platinum electrodes that you put in water, send a current through, and you get hydrogen and oxygen. As you can see, red doesn't even come up on that plot. So currently, it's all fossil-based, not much to pretty negligible amounts of electricity. But we're also going to need a lot more of it. So the middle part of this graph shows that currently we're using 95 million tons a year. To get to net zero 2050, we need to be between 4 to sometimes 8 times as much demand, depending on the scenarios. So if you're looking at really ambitious scenarios from the ETC, they say 800 million tons a year. Bloomberg, who we use a lot of data from, around about 390. But yeah, we're going to need around 4 to 5 is a comfortable amount times increase in the amount of hydrogen we need for new sectors, new applications. And this is mainly driven by industry, fertilizer, and kind of hard to abate sectors you could group these into. And this is like I was saying earlier, you need a molecule for fertilizer. You can't electrify plants to make them grow. You have to use molecules and nitrogen-based fertilizer. aviation and shipping, it's more about energy density. So with aviation, you're fighting against gravity. You need something that's got a good gravimetric energy density. You can't use batteries for that, so you're going to have an alternative. At the moment, smaller flights, we can go into more detail later on, smaller flights might be able to use hydrogen as a gas in a fuel cell powertrain, but at the moment it's going to be ESAF, so sustainable aviation fuel, or synthetic kerosene made from captured carbon and hydrogen. So I said we're a commercial bank, we're interested in the commercials. To get to those kind of figures, we're looking at between 10 and 15 trillion dollars US of finance needed, or of investments needed by 2050. So significant opportunity for the bank. And going back to that question at the start, why do we care about hydrogen? It's because we need it for net zero and there's commercial opportunity there. So I can skip through some of these that won't interest the academics and try and skip to the ones that maybe do. But this is the Asia outlook for demand. So it's what I was saying before, but specifically for Asia. There's existing use cases. I was talking about the ammonia, the oil refining, the methanol. They're the existing use cases that we can try and decarbonize now. And as you can see, we're going to try and tail away from the gray hydrogen production mechanisms and try and ramp up green, which is electrolytic, or blue, which is carbon capture. But then there's these new use cases that we're going to need. In Asia, most of it's going to be steel. So the way the steel industry works, there's primary steel and secondary steel. Secondary steel could be done with electrification. So you can use scrap steel and use electric arc furnaces powered by renewables or geothermal. You can use that to melt that steel down. But the primary steel, where you're trying to get the iron out of the ore, you need a molecule, you need that reaction, you need the reducing agent. So where hydrogen plays a role is, instead of using coking coal that we use now to A, generate the heat you need for the steel mill, but B, to actually sap the iron out of the ore, you can replace that with hydrogen. And if that hydrogen is renewable, you can vastly reduce the emissions from the steel industry, the primary steel industry. So there's going to be a mixture of hydrogen use and electric arc furnaces. But a big opportunity, specifically because if you look at places like India and China, a huge amount of steel production. So a good opportunity there to decarbonize. And then we've got all these other new use cases that are a bit smaller chunks, but still really important. As I said, like power sectors, aviation, big, heavy, hard to decarbonize sectors. On the right-hand side, we can see from this new uptake in demand, most of it's going to be electrolytic. That's kind of the gold standard from an emissions perspective. So if you use renewables into electrolyzer, there's no carbon emissions. As I mentioned before, blue does still have a carbon intensity associated with it, so it's a bit trickier to fully clean up, but it is cleaner than the counterfactual. If we drill down into Indonesia, so I was going to use this slide today. It's a little bit, it's not finished. It's not the way I'd like to present it, so forgive the presentation, but the information is interesting. So when I said Asia and globally, it's about 5 times increase. In Indonesia, because we're starting from a smaller number, there's about a 14 times increase, and that's a mistake, to 2050. So to get to 2050, Indonesia is looking like it might need to upscale by 14 times. And these are the different sectors that are predominantly the focus for Indonesia. So mainly it's looking at aviation fuels, road transport, steel industries in there, and a little bit of ammonia production as well. And we've been speaking to companies today at the event, looking at where their interests lie in these different sectors. And most of that, again, is going to come from electrolysis. The thing with Indonesia is it's very blessed with abundant renewable options. You've got geothermal everywhere. You've got good solar capacity factors in the south. You've got good wind capacity factors. You've got hydro. You've got a choice of ways to use renewable power for hydrogen production. So why would you look at blue? This is what I was going to present today as well about the Southeast Asia ecosystem. So it's not just about how can one country decarbonize its own energy or carbon intensive industries. It's how can you play a role in a broader ecosystem. So this is for Southeast Asia. And again, it's different use cases. So steel is a bit more important than just in Indonesia, and shipping is a big chunk. So to decarbonize shipping, and we were just talking earlier about emissions like NOx emissions, shipping is really tricky. It uses heavy fuel oil at the moment. And again, it can't really use batteries. For big shipping containers, at least, you need a kind of molecule. It's looking like it might be something like methanol produced from hydrogen and a carbon capture, or ammonia. So shipping is going to be really important in Southeast Asia, and there's going to be multiple hubs that are required to produce and store green ammonia or green methanol to fuel these vessels. Next up is kind of a lot of data on one slide, but this is basically showing where we are seeing as a bank, where are the off takers for these projects. So we know hydrogen is important. We know a lot of companies are trying to get investing in this space. Where's it actually happening? What's the real world scenario? So if we focus mainly on the left-hand side, we can see that the top 15 off-takers by volume, so people or companies that have signed off-take agreements for clean hydrogen or clean ammonia or clean methanol, the derivatives of hydrogen, it's all like I was saying before. We've got steel. So POSCO is a big steel manufacturer. We've got Sinopec in China that's in oil refining. Fertiberia, so we've got Yara on fertilizers. So it's the heavy industries that we talked about earlier that are really committing to this and signing agreements. And it's the same kind of thing in the picture for the amount of deals that they're doing. Most of this is driven by EU. So at the moment, there are subsidies to support the production of this because this is expensive. So green hydrogen is a far more expensive way to produce the molecule than conventional methods. But in the EU, there's mandates where you have to do something, but also there's subsidy mechanisms to reduce the costs. So that's why we're seeing a lot of activity in the EU. Most of this is quite long term. So if you think of people in the room that might be experienced with oil and gas or the LNG world, you kind of have spot markets or short-term contracts. You might buy a volume of gas over a year. With hydrogen, there's no liquid market at the moment. So it's looking like really long deals. We did a deal in Saudi that was 30-year contract, but it's looking like between 10 and 20 years is what a project contract might look like. So someone's going to have to say, I will buy a certain amount of green hydrogen over the next 20 years at this price. So it's quite tricky commercially for us to get our heads around. So fertilizer is the no-brainer, right? So there's a prioritization of where you'd use hydrogen. Hydrogen you can use anywhere you need heat or anywhere you need electricity. You could use hydrogen, but why? But would you? And there's a kind of a conflicting priority list. Electrify if you can. It's the most efficient way of doing it. It's the cheapest way. Solar and wind, it's really cheap now, easy to deploy at scale. But fertilizer is the no-brainer. As I said earlier, you can't electrify your crops. And as we can see here, we'll start on the left-hand side. So Haber-Bosch process was discovered around 1900, I think the start of this plot. And it's the way of using nitrogen from the air. So you use like either pressure swing absorption or you use cryogenic separation to get nitrogen from the air. And then you mix it with hydrogen, which normally is from the fossil route. But when you mix your nitrogen and hydrogen, you get ammonia. So ammonia is used to then turn into urea, to turn into fertilizers. But predominantly, we're saying that pretty much half of the global population is now propped up by the fertilizer industry. So as we fertilized crops, got higher yields, it supported global growths in population. So we can't just stop this. We can't say, right, we're going to stop using fossil-based fertilizer. These people need to be fed. And 2% of global emissions is quite significant. And we can decarbonize that using clean hydrogen. So it's something that we have to do. We're doing it now. All we have to do is replace that hydrogen that's going in with a clean version. But not only that, so we use around, we produce around 185 million tons of ammonia per year for this fertilizer. Most of it goes into the fertilizer application. We're also going to need more of it. So these are two different scenarios from, I can't remember the source, IEA, I think it's the IEA. They say that we're going to keep using ammonia for fertilizer production, but we're also going to need it for maritime fuels and power generation. So as I was talking about before, maritime's really tricky to decarbonize. Ammonia is one of the front runners for a fuel that could decarbonize that. It's going to need a different technology, so a different kind of combustion engine, a two-stroke engine, but they are being developed now. And then power generation, I'm not counteracting what I said before about you should electrify everything if you can. Sometimes you can't. So a good example is in Southeast Asia. So say for Singapore, for example, really constrained on land, you can't just put renewables all over Singapore. There's not enough space. So how do you decarbonize Singapore's power sector? You might say, well, why don't they get renewables from their neighbors and use a high voltage cable? But they can't do that because of energy security concerns. So there's going to be some regions that need ammonia to be burnt in turbines to use as power generation. So it's going to play a role where you have these nuances of yeah, you can't roll out the renewables for a variety of geopolitical reasons or logistical reasons. That's where it will play a role. So fertilizer is a no-brainer. That's one of the things that we definitely will support and should be at the top of the list. Next up is what I was talking about with steel. So this is from Bloomberg data. How do we get to 2050? And as I was saying, predominantly we're looking at direct reduction with hydrogen. So this is using hydrogen as the reactor, the reducing agent, but also as potentially as the heat source to produce primary steel. Secondary steel can be scrap with electric arc, so you can use renewables to melt the steel. One interesting one where there's a lot of research that's interesting to watch, and at the moment it's only playing a tiny sliver of a role, is molten oxide electrolysis. So very early stage, very low TRL, very much at the academic research stage. But this is looking at using electrification to power a molten oxide electrolyzer. So it's a different kind of, if you think of all electrolyzers have an anode, a cathode, and a separator, it's a different chemistry to what we're used to with low temperature electrolysis that we're using now. But something to definitely keep an eye on because it could play a crucial role in replacing the need for hydrogen and scrap EAF. Aviation, another one that is hard to decarbonize. So these are two scenarios. So one is if biofuels get cheaper and rolled out at scale, and the other one is there's a feedstock constraint on biofuels and hydrogen takes off. So two ways that hydrogen is going to play a role. As I said, hydrogen can be either burnt in a turbine or electrochemically converted in a fuel cell. They can be used for aviation of small scale planes. So if you think of an aeroplane that might be 20-seater to 40-seater, so relatively small, but like regional transportation, you could use hydrogen in gaseous form. When you go up to the bigger kind of the flight that got me here, that's going to have to be a sustainable aviation fuel, but you still, it's called power to liquids, but you still use hydrogen to produce that. So you get your hydrogen from somewhere, you get your carbon from somewhere, you use the Fischer-Tropsch process, and you produce a synthetic kerosene. That's a drop-in fuel for the aviation industry. So on the right-hand side, that could be hydrogen playing 55% of the role of decarbonizing aviation by 2050. But even if biofuels are more rolled out more predominantly than hydrogen, even then it's still 29%. So to decarbonize aviation, hydrogen is going to play a huge role. Lots of research opportunities there. I think there's some stuff recently about, so you're going to have to cryogenically cool hydrogen, so minus 253 or whatever it is. So when you've got liquid cooled hydrogen to get enough energy density on board, you can use that heat, well, the lack of heat, to cool the motors in the propellers, for example, and you can increase the efficiency of the powertrain by using that as you boil off or as you get the hydrogen back into gaseous form. You can use that temperature difference to increase efficiency of powertrain. So lots of innovation happening in the aviation world. Maritime, different picture, but same kind of message is currently we use a fossil fuel. We need to move away from that. Biofuels probably won't play a huge role. And it's going to be a kind of competition between ammonia and methanol. There's pros and cons for each, and I personally think we're going to see them split between different types of maritime. So if you think of passenger ferries where you've got 100,000 people on a ferry, you probably don't want ammonia on there because it's very toxic. If it leaks, a lot of people are going to die. But if you're on a container ship that's huge and you've got a crew of 5 and you can contain the engine room, ammonia is probably good for that. So it's going to be different. One's a carbon-based synthetic fuel, one's a nitrogen-based, and they're going to play different roles. And as we can see, big companies like MOL, they've got a strategy that shows as they move out to 2050, ammonia is going to play a huge role for their shipping. Some bio might play a role, or E-based, synthetic-based methanol. So one slide that I sometimes don't present in the bank because it would bore bankers, but I'm hoping will land well with you guys because you're academics. Because it has an equation, all right? I'm itching to stay involved in the academic world, and I try and drop things in when I can to make an argument. So this is the argument for power. So we talk to a lot of companies who are looking at decarbonizing their power generation by burning hydrogen in a natural gas turbine or burning ammonia that was made by the hydrogen into a coal facility. And this is where it shows that, yes, if you move up towards 100% volume of hydrogen burnt in a power turbine, you can reduce your emissions. So the 100% reduction in carbon comes with 100% blend. But the problem is it's a non-linear curve, right? So hydrogen, because of energy density or the lower heating value difference between methane and hydrogen, sorry, the volumetric difference means that you need to put in about 3.5 or 3.3 times as much flow rate of hydrogen to get the same amount of calorific value for the burn. So when you hear companies saying we're going to put 20% blend of hydrogen into our turbines to reduce emissions, it might sound great, but if you run the numbers, 20% blends around at this point, or 30% blends, you're still not even reducing 20% of your emissions. Sorry, up to 50% blend rate by volume, apologies, is 25% reduction in emissions. So you kind of need to be getting up into this range to make a material impact or more than 50% reduction, but then you're up to 80% blend rate to 100. So this is the same thing for ammonia into coal power reduction. You need to be at the real upper end of those blend rates up to 100% to really make a difference. And that's costly. So at the minute, natural gas or methane is quite cheap, but it's carbon intensive. Hydrogen's quite expensive and you need 3.3 times more of it. So it's a really tricky problem with the power sector. So that's why it's at the lower end of the priority list, but we don't rule it out because, as I said, some people, some regions, some situations require this alternative. A brief one on energy density. I just threw this in just before the talk because I thought it was important to note. Everything I've said, it kind of says the same thing. It's based on this energy density conundrum. So where you're using diesel in road transport or using kerosene in aviation or whatever it might be, it's got a much better gravimetric energy density, so the amount of energy you get for the weight of the fuel, and volumetric energy density, like how much space it takes up. Hydrogen gas is awful in terms of volumetric energy density, right at the bottom of the curve. If you compress it to about 700 bar, which is, I can't remember the conversion, is it like 14,000 psi or something? So really high pressure, you might be able to get it a little bit up on the volumetric energy density curve. But even so, it's still pretty bad. If you liquefy it, you can bump it up a little more, but it's still quite bad. So that's where, as I was saying, you need to prioritize where you use hydrogen, where you use liquid hydrogen, where you turn it into a derivative, and where you use that. And there's a multitude, like a multifaceted picture you have to build up of what's my application, where am I producing the hydrogen, where am I going to use it, in which sector, and it makes it difficult for us in the bank to look at different projects, different companies, different technologies, because there's no easy broad brush to say, yes, this thing works. You have to look at it in every detail of what location is it in, what asset, what use case is it in, what's the government policy, all these kind of things. So they keep me very busy. Indonesia, we kind of touched upon this at the start. So this is something that I didn't present today, and I'm quite happy I didn't, because this is the way we normally look at hydrogen production. So where you're going to make it, the levelized cost of hydrogen is mainly made up of the price of the electricity you use for the electrolysis, and the other part is the capex. So these are the two biggest contributors to the cost. So what we normally do is look at this. We map out where's the best solar irradiation, where's the best wind profile, and where's all the water. If those things all line up, that's where you should be producing your hydrogen. But this is kind of like a Eurocentric view. And when I came here and I was on a panel this morning, I heard about the immense geothermal potential and the hydro that is in Indonesia. So Indonesia bucks the trend on this, even though it makes the same point. Capacity factor is a huge thing. So the technology, electrolysis itself, wants to be used at a steady state or a base load. So this is where finally I get to use my PhD in the corporate world, is the degradation that's caused to electrolyzers, specifically PEM or alkaline, whatever chemistry it might be. They don't like transient loads and they don't like stop-start cycles. So if you have a project, say for example, that has really good solar potential, but only for 4 hours of the day. So it comes on, electrolyzers for a while, dips off. That's really bad for the electrolyzer. It's going to keep degrading the electrolyzer. It's probably only going to last like 1 year or 2 years. And then you have to replace it, and they're very expensive. So the whole capex for the project goes up. So what you need to look for is somewhere like Indonesia that has geothermal with a really high capacity factor. So 90% capacity factor means you're running it most of the time. You can plug that into your electrolyzers, have very minimal stop-start cycles, very minimal transient loads. And those electrolyzers then are going to last maybe 10 years, 15 years, and that could be the lifetime of the project. So it brings the commercial picture for us is a lot about how are people using this technology. It's not a new technology. Electrolyzers have been around for 100 years. It's how you operate them and the synergies you have with different components. We spoke about ammonia synthesis using the Haber-Bosch process. That a lot of heat is generated in that. So you could use a new type of electrolyzer like solid oxide technology. Again, been around for a while, but much lower TRL. It's not really been deployed at the gigawatt scale, but that needs a heat input. So it's basically steam electrolysis. It needs high temperatures for the materials inside. There's like zirconia. There's different materials inside, like ceramics. Basically, they need to be very hot to work. So you could use the heat that comes out of the Haber-Bosch process to feed into your solid oxide electrolyzer and increase the overall efficiency of the system. So there's different ways that now I think companies are going to be having to look at different innovative solutions out of the research and development world that can really increase the efficiencies of production and reduce those costs. Other than that, this is policy, but that could be boring, so we'll skip that. That's boring. So this is emissions intensity. So I was kind of talking about this at the start, and sorry that we're kind of going backwards and forwards, but this is about different colors on the left, but we're moving towards a more carbon intensity metric. So depending on where you are in the world, if you plug an electrolyzer into the grid, you could be very, very carbon intensive. So if your grid is 100% coal, you're going to be up this end. If you're in, where's good? Norway, Denmark, those kind of places that are all hydro, you're going to be down this end. But if you're dedicated wind or solar, there's no emissions. With carbon capture, this is what I was saying earlier. So if you only have a 60% capture rate, your emissions can be quite high. You might be able to use partial oxidization with CCUS to get up to 99%, but that's still theoretical. But also what we've noticed is it's not just the capture rate that's important with carbon capture, it's the upstream emissions leakage. So if you're using natural gas in your process, but you've got a load of leaks as the gas comes in, that's got a really high, obviously methane has a much higher greenhouse gas intensity than carbon. That's going to bump up your emissions as well. So it kind of reinforces the fact that the focus should be on electrolysis. And then costs. I think we'll finish up on costs because I think it'd be great to have a discussion and have some questions and talk about some research and development opportunities in the space. But finally on costs. So these are two plots that show the picture last year and the picture in 2030 of different regions and how cheap or expensive you can produce hydrogen in US dollars per kilogram. Indonesia's up here, which is not great news, I'm afraid. Is at the moment, if you're using, I think, yeah, so solar PV is the red part. The bottom of this plot is if you use the cheapest electrolyzers that are on the market. These are coming out of China, very cheap. Old, well, no, I won't say old. Conventional technology, so like alkaline-based electrolysis. At the top end are Western PEM manufactured electrolysis stacks. So it's a different technology. They use more precious metals in the catalysts, more expensive. But depends on, as I said, where's your solar? This is averages as well. So average over Indonesia is not that great, but Java region is really good. And this shows that over time, these bars start to converge because electrolysis manufacturing gets cheaper, the scale up of production brings the economies of scale down. And then the last thing I'll say is on the blue hydrogen angle. So we will support blue projects if they reduce carbon emissions, but the issue is you are linked to the price of natural gas because obviously it's natural gas with carbon capture. And this is a plot that shows the price of natural gas over the past few years and what happened with recent geopolitical events in Europe pushed the price so high of natural gas that blue hydrogen was way more expensive than electrolytic will ever be. So there's a price volatility issue with linking to blue hydrogen production. And these are just some figures of how that is played out across the world. So that was a bit of a slapdash, in a nutshell, hydrogen view. Some of it was from the commercial angle. Hopefully some of it had a bit of an R&D angle. But from what I'm seeing from our perspective, that we'd really appreciate a lot of help from the academic world is both on, I've mentioned some low TRL technologies. So there's a lot of chemical engineering that needs to be done, a lot of chemistry on catalysts and different materials, also for storage of hydrogen transportation. So there's companies now that are proposing to look at scaling up or spinning out of universities technologies in liquid organic hydrogen carriers. So how do you, because of we said volumetric and, well, mainly volumetric energy density for hydrogen is really bad. How can you bind that in either an organic framework or an organic hydrogen carrier? How can you get that hydrogen from where you made it to where you need it most efficiently, most cost effectively? So there's different ways to store hydrogen and transport hydrogen that are in the research stage. But also on the other end of the scale is the techno-economic modeling of these systems. So as I said, at the moment, I think a lot of companies are proposing to deploy renewables into electrolysis using a derivative synthesis process that are all known things. Like, we know electrolysis, we know Haber-Bosch, we know all this stuff, and just bolting it together. That will work for now, first of a kind. But how do you get the systems to be most efficient? How do you get the synergies of waste heat from one process going into another process? So there's lots of systems level modeling and thinking that I think would really help reduce the cost of these derivatives and these molecules, which would help accelerate the commercial viability of them in certain regions. So I hope that was of interest, and I'm keen to hear questions, thoughts, areas of improvement, whatever you suggest.